Egyptian faience is often mistaken for an early form of ceramic, but it is something far stranger and far more precise. Long before true glass-making or glazed pottery became common, ancient Egyptian artisans developed a material that created its own glassy surface during firing. At its core, faience is primarily crushed quartz. Silica, in its purest workable form, mixed with small amounts of alkali fluxes derived from natron or plant ash, along with copper-based compounds responsible for its iconic color. When fired at temperatures between roughly 800 and 950 degrees C, the material behaves in a way that still challenges modern replication. Instead of requiring an applied glaze, faience generates a vitreous coating from within. As heat rises, alkali salts migrate outward through the porous quartz body. At the surface, they interact with copper compounds and silica, forming a thin glass layer rich in copper silicates. This self-glazing process produces the intense turquoise and deep blue tones seen on beads, tiles, and figurines spanning more than 3 millennia of Egyptian history. Scientific analysis has revealed how finely tuned this process was. Microprobe studies of artifacts from Abydos show copper concentrations in the glaze ranging from 4 to 7% by weight. Beneath the surface lies a narrow transition zone where silica content rises sharply from about 60% in the glaze to over 80% in the core. This gradient is not accidental. It indicates a controlled diffusion process that modern kilns struggle to reproduce consistently. Experimental reconstructions have demonstrated just how sensitive faience production is. Controlled atmosphere kiln tests show that even slight changes in oxygen partial pressure, shifts as small as 0.01 to 0.03 atmospheres, can dramatically alter glaze opacity and color saturation. Too much oxygen and the blue dulls. Too little and the surface becomes patchy or opaque. Ancient artisans achieved uniform results without modern instrumentation, suggesting an empirical mastery of firing conditions that remains difficult to match. Today, researchers at institutions such as the Getty Conservation Institute are using laser-induced breakdown spectroscopy to observe glaze formation in real time. Their work focuses on identifying firing profiles that reduce defects while exploring environmentally safer flux alternatives, including sodium-potassium borates to replace mined natron. Experiments with microscale layering have even produced prototype tiles with gradual color transitions echoing the natural gradients seen in ancient pieces. Despite these advances, modern replicas rarely capture the exact texture, luminosity, and depth of true Egyptian faience. The chemistry is understood, the temperatures are known, yet the balance achieved by ancient craftsmen between material, heat, and atmosphere remains only partially within reach. The south-pointing chariot is a marvel of ancient engineering that defies simple explanation. First appearing during the Zhou dynasty around the 4th century BCE, it was designed not merely to transport people or goods, but to maintain a constant orientation toward the south. Unlike magnetic compasses, which were not yet in use, this two-wheeled invention relied entirely on mechanical ingenuity, translating the rotation of wheels into the directional control of a pointer. No matter how the chariot turned or twisted over uneven terrain, the pointer remained steadfast, always indicating the correct direction. The chariot's mechanism is rooted in the principles of differential gearing, a concept modern engineers recognize as fundamental, but that was astonishingly sophisticated for its time. As the wheels rotated at different rates during turns, a series of gears and shafts transmitted the motion to the pointer. This ensured that the angular displacement of the chariot itself did not affect the orientation of the pointer. Historical texts describe the device as a demonstration of precision, science, and ingenuity, capable of guiding armies, travelers, and emissaries over long distances in an era without standardized maps or compasses. Yet the precise workings of the original south-pointing chariot remain elusive. No complete examples have survived the centuries, and written accounts are fragmentary. Later reconstructions, including European adaptations in the 18th century, attempted to replicate its principle, but each iteration introduced modifications, simplifying or altering the original gearing and proportions. While modern scholars can create functional models that mimic the concept, these reproductions cannot capture the exact scale, efficiency, or subtle mechanical tolerances of the original. The chariot exemplifies a principle now taken for granted in engineering: non-magnetic orientation. It demonstrates an understanding of motion, translation, and feedback control that predates similar Western concepts by centuries. Observers of the time reportedly regarded it as both a practical tool and a wonder, a mechanical solution to a problem that even modern technology approaches differently. What makes the south-pointing chariot enduringly mysterious is its combination of simplicity and sophistication. The concept can be explained in theory, yet the craftsmanship required to produce a working model, one that performs reliably under real-world conditions, is nearly impossible to recreate without modern machinery. For all our advances in precision engineering and robotics, the ancient Chinese chariot remains a symbol of lost knowledge, an invention whose elegance continues to confound and inspire centuries after it first rolled across the landscape. If these stories of ancient ingenuity have changed the way you look at the history of technology, please subscribe to our channel and like this video. We are unearthing the history that time tried to bury. Help us plant the seeds for the future. The next treasure of the past will be revealed soon. The Nimrud lens is a small, unassuming object, yet it unsettles historians more than many monumental ruins. Discovered in the mid-19th century among the remains of the Assyrian city of Nimrud, the artifact dates to roughly the 7th century BCE, during the height of the Neo-Assyrian Empire. At first glance, it appears simple: a piece of carefully shaped rock crystal, slightly convex, polished to a clarity that feels deliberate rather than decorative. But its implications are anything but simple. The lens is made from quartz, a material that must be worked with patience and precision. Unlike softer stones, quartz resists shaping and fractures unpredictably if mishandled. Microscopic examination shows that the Nimrud lens was ground and polished in a controlled multi-stage process. The curvature is uneven yet functional, capable of modest magnification. When tested under modern conditions, it enlarges small details enough to sharpen fine lines and edges, just enough to matter. This raises an uncomfortable question. Why would an ancient Assyrian craftsman invest so much effort into producing an object with optical properties? Some researchers argue it was simply decorative, perhaps an inlay or ornamental fitting. Others note that its focal length and magnifying ability are consistent with practical use. It could have assisted artisans engraving seals, carving ivory, or working fine metal filigree, tasks the Assyrians were famously skilled at. More controversial suggestions have followed. Some scholars have proposed that it may have been used as a primitive magnifier or even as a fire-starting tool by concentrating sunlight. These interpretations remain debated, not because the lens fails optically, but because written records describing its use have not survived. Assyrian texts catalog tools, materials, and rituals in great detail, yet none explicitly mention lenses or optical devices. What makes the Nimrud lens especially puzzling is that it appears technologically isolated. There is no clear lineage leading to it and no obvious tradition following it. Comparable lenses do not appear again in the archaeological record until much later in Greco-Roman contexts. The knowledge required to produce it seems to surface briefly, then vanish. Modern scientists can replicate the shape of the lens, but recreating its context is harder. Without knowing how it was used, replication becomes guesswork. Innovation without documentation leaves no roadmap. The Nimrud lens stands as evidence that ancient societies sometimes reach solutions that history did not preserve, advances that worked well enough to exist, but quietly enough to be forgotten. Roman concrete does not fail the way modern concrete does. That is the uncomfortable fact confronting engineers who study the remains of ancient harbors still standing after nearly 2,000 years of constant exposure to waves, salt, and pressure. Structures at sites like Pozzuoli Bay were not merely durable, they were chemically alive. The Romans produced their maritime concrete by combining lime with volcanic ash, known as pozzolana, then mixing the binder directly with seawater. Unlike modern Portland cement, which weakens in saline environments, this mixture hardened underwater and grew stronger over time. The key lies in how the material responds to damage. When microscopic cracks form, seawater seeps into the concrete rather than destroying it. That intrusion triggers a slow chemical cascade instead of structural decay. Within those fissures, seawater dissolves residual calcium hydroxide and unreacted lime particles trapped in the matrix. These dissolved minerals then interact with silica and alumina from the volcanic ash. The reaction precipitates aluminum tobermorite, an exceptionally stable crystalline mineral rarely formed under ambient conditions. Petrographic analysis of cores extracted from Roman piers reveals distinct layers of these crystals lining cracks, sometimes reaching thicknesses of up to 150 micrometers. Rather than spreading, the cracks are sealed from the inside. Modern imaging techniques have confirmed this process. X-ray diffraction and scanning electron microscopy show that crystal growth continues long after the initial curing phase, sometimes over decades. The concrete does not simply resist damage, it responds to it. Each fracture becomes a site of mineral reinforcement, locking the structure into greater stability. Attempts to recreate this behavior have met limited success. Contemporary researchers at institutions such as MIT and the University of Toronto are experimenting with biomediated self-healing systems. One approach embeds ureolytic bacteria, such as Sporosarsina pasteurii, into concrete mixes. When water enters a crack, the bacteria activate and hydrolyze urea, producing carbonate ions. These combine with calcium to form calcite, sealing fissures up to half a millimeter wide. Another method uses microcapsules filled with calcium lactate or other mineral precursors that rupture under stress. These techniques can close cracks, but they do not replicate the Roman chemistry. Modern systems heal damage intermittently. Roman concrete reorganizes itself at the molecular level. Field trials on bridges and marine infrastructure are underway to measure long-term performance, energy costs, and durability. Yet, even as modern concrete learns to repair itself, it still lacks the quiet permanence of the ancient formula. Roman builders did not know the names of the minerals they created, but the structures they left behind suggest they understood something fundamental. That in the right conditions, stone does not just endure time, it adapts to it. Wood steel did not look extraordinary when it left the furnaces of southern India. It appeared as small, dark ingots, dense, unassuming, and easy to overlook. Yet once forged, these ingots became the raw material for some of the most feared and admired blades in history. Known later as Damascus steel, weapons made from woods combined an edge sharp enough to slice silk in midair, with a toughness that resisted shattering under impact. For centuries, no other steel matched this balance. The origins of wood steel date back to at least the 3rd century BCE. It was produced by melting iron with carbon-rich organic materials inside sealed crucibles, allowing carbon to dissolve uniformly throughout the metal. This high-carbon steel solidified slowly, forming a distinctive internal structure before any forging even began. The real mystery lies in what that structure became. Modern analysis has peeled back part of the secret. Using transmission electron microscopy and atom probe tomography, scientists studying surviving Wootz blades have identified networks of carbide nanoparticles concentrated along grain boundaries. These carbides are not random. They are enriched with trace elements such as vanadium and molybdenum, present in minute quantities but critical in effect. Positioned where cracks normally spread, these particles block fracture paths, allowing the blade to absorb stress without failing. The iconic surface patterns associated with Damascus blades are not decorative accidents. They emerge from repeated thermal cycling and careful forging. As the metal is heated, cooled, and folded, hard cementite faces organize into bands within a softer ferrite matrix. The result is a natural composite material, hard where sharpness is needed, flexible where shock must be absorbed. Reproducing this balance has proven difficult. Modern metallurgists can make steel harder, they can make it tougher. Achieving both simultaneously without sacrificing reliability remains elusive. Researchers at institutions such as the University of Manchester's Henry Royce Institute and Tohoku University are now attempting controlled recreations using powder metallurgy and laser-based additive manufacturing. These methods allow unprecedented control over composition and cooling rates, sometimes regulated to within 1 degree C per second. By introducing vanadium at concentrations as low as 0.03% and mimicking ancient cooling profiles, Experimental blades have reached hardness levels exceeding 65 on the Rockwell scale while maintaining impact toughness comparable to historical specimens. Differential scanning calorimetry of authenticated wood samples is helping refine tempering schedules, offering clues about how ancient smiths guided phase transformations without instruments. Yet even with modern laboratories, success is inconsistent. Wootz steel was not just a recipe, it was a process sensitive to time, temperature, and trace impurities. The knowledge survived in blades, not in texts. And once the trade routes faded, the technique vanished with them, leaving behind steel that modern science can analyze but not reliably recreate. Maya blue is not just a color, it is a chemical anomaly that endured for centuries in one of the harshest environments imaginable. From around the 3rd century CE onward, this vivid blue pigment appeared on murals, ceramics, sculptures, and ritual objects across Mesoamerica. Rain, heat, humidity, and even acidic conditions that erased other pigments left Maya blue almost untouched. When archaeologists first encountered it, they assumed it must be mineral-based. It wasn't. The pigment is organic at its core. Its color comes from indigo, the same dye derived from plants that fades easily when exposed to light and weather. On its own, indigo should not survive outdoors for decades, let alone centuries. Yet in Maya blue, it does. The reason lies in an unusual partnership between the dye and a rare clay mineral known as palygorskite. Palygorskite has a fibrous, channel-like structure at the molecular level. During the production of Maya blue, indigo molecules are heated together with this clay. At elevated temperatures, generally estimated between 150 and 200 degrees C, the indigo diffuses into the microscopic channels of the clay. There, it becomes physically trapped and chemically stabilized. Hydrogen bonds form between the dye and the clay lattice, locking the color in place. This process fundamentally alters the behavior of indigo. Once embedded, it becomes resistant to acids, solvents, microbial decay, and ultraviolet radiation. Laboratory tests show that authentic Maya blue can withstand exposure to nitric acid without significant color loss, something no ordinary organic pigment should survive. Despite knowing the basic ingredients, exact replication remains elusive. The pigment's stability depends on precise conditions: the purity of the palygorskite, the molecular state of the indigo, the heating duration, and the temperature profile. Too little heat and the dye washes out. Too much and the indigo decomposes. Small deviations alter hue, durability, or both. Modern attempts have produced visually similar blues, but they often fail long-term stability tests. Replicas may look correct when fresh yet fade or chemically degrade under conditions that original Maya blue endures effortlessly. Part of the challenge lies in natural variability. Ancient clays differed subtly in composition depending on their source, and the indigo was derived from plants processed using methods that are no longer fully documented. Equally mysterious is how consistently ancient artisans achieved this result without thermometers or chemical theory. The pigment appears across vast regions, suggesting a shared and reliable technique. Yet no surviving texts describe the process in detail. Maya blue represents more than artistic mastery. It is evidence of a deep empirical understanding of materials, one that modern chemistry can analyze but still struggles to fully reproduce. In the year 132 CE during the Eastern Han Dynasty, a scholar named Zhang Heng unveiled a device that challenged how humans understood the Earth itself. It was called the Hufeng Didong Yi, often translated as the world's first seismoscope. Cast in bronze and shaped like an ornate vessel, it was designed not to predict earthquakes, but to do something far more unsettling for its time: to detect distant seismic events that could not be felt or heard. The device stood nearly 2 meters tall. Around its exterior were 8 sculpted dragon heads, each holding a bronze ball in its mouth. Beneath them sat 8 toads positioned to catch the falling spheres. According to historical records, when an earthquake occurred hundreds of kilometers away, one dragon would release its ball, indicating the direction of the tremor. Contemporary accounts claim the device detected quakes so distant that officials felt nothing locally. Yet later reports confirmed seismic damage in the indicated direction. What makes the seismoscope mysterious is not its purpose, but its mechanism. No surviving diagrams exist. The original device was lost, and Zhang Heng's writings describe the outcome, not the internal design. Later, Chinese texts confirmed that the instrument worked but remained vague on how. This absence of detail has turned the seismoscope into a mechanical puzzle that has resisted definitive reconstruction. Most hypotheses center on an internal pendulum or inverted pendulum system. A slight ground motion would shift the pendulum, triggering a linkage that released a single ball while leaving the others untouched. Achieving that level of directional sensitivity without springs, electronics, or precision bearings is extremely difficult. The material properties of the bronze, the mass distribution, and the damping behavior would all need to be perfectly balanced. Modern attempts to recreate the device have produced mixed results. Several replicas built in the 20th and early 21st centuries demonstrated basic directional triggering, but often responded to local vibrations rather than distant seismic waves. A reconstruction by the Chinese Academy of Sciences in the early 2000s successfully dropped balls, but critics noted that its behavior did not fully align with historical descriptions, particularly in distinguishing weak, far-off earthquakes from nearby disturbances. Unlike modern seismometers, which rely on digital sensors and signal filtering, Zhongheng's operated purely through material response. Its effectiveness depended entirely on mechanical thresholds embedded in metal. Thresholds tuned so finely that even today, they are difficult to reproduce reliably. The Chinese seismoscope represents a lost intersection of materials science, mechanical intuition, and empirical observation. It was not just a device, but a system calibrated to the Earth itself. Modern science understands earthquakes far better than Zhang Heng ever could. Yet the precise material logic that allowed his bronze vessel to listen to the ground and respond correctly remains only partially understood. The Lycurgus cup is not merely a relic of Roman glassmaking. It is a demonstration of technology so advanced that it still astonishes modern scientists. Crafted in the 4th century CE, the cup appears unremarkable at first glance. A deep green vessel adorned with intricate reliefs depicting the myth of King Lycurgus. Yet its true marvel is revealed when light interacts with it. Viewed in reflected light, the cup glows green, but hold a light source behind it, and the same glass transforms to a vivid ruby red. This dramatic effect is not the result of pigments or paint, but of nanoscopic metallic particles embedded within the glass matrix. Gold and silver nanoparticles, no larger than a few dozen billionths of a meter, scatter and absorb light selectively, creating what physicists today describe as dichroic behavior. Essentially, the artisans of late antiquity had discovered a form of nanotechnology long before the term existed and without the benefit of microscopes or electron beams. The exact methods used to achieve this effect remain unknown. Researchers have deduced that the glass was heated with precise control, likely multiple times, and that trace amounts of gold and silver salts were carefully introduced during melting. The particles had to nucleate and grow to specific sizes. Too large, and the color would shift. Too small, and it would disappear entirely. The result was a glass that not only transmitted light differently depending on angle and illumination, but did so consistently across the cup's complex three-dimensional surface. Modern attempts to replicate the Lycurgus effect succeed in principle, but the challenges of stability, uniformity, and scale remain formidable. Even with controlled furnaces and nanochemistry, creating a vessel that matches the color shift, translucency, and clarity of the original has proven elusive. Any deviation in temperature, timing, or particle concentration can ruin the delicate balance. The ancient artisans achieved this without written manuals or experimental records, relying instead on empirical observation, experience, and perhaps generations of trial and error. The cup also raises questions about purpose and understanding. Was the dichroic property an intentional technological achievement, a display of luxury, or both? The precise knowledge of metals, heat, and glass chemistry required implies a sophistication in Roman workshops that rivals modern laboratories in conceptual ingenuity, even if not in instrumentation. The Lycurgus cup remains not just a work of art, but a testament to the ingenuity of ancient craftspeople. Its shifting hues are evidence that millennia ago, humans were capable of manipulating matter on a scale that continues to challenge and inspire contemporary science. It is a mystery both beautiful and insoluble, a small cup that continues to reflect the brilliance and the enigma of antiquity. Long before the Industrial Revolution and the invention of modern vulcanized rubber, pre-Columbian Mesoamerican societies were already shaping resilient, elastic materials from the sap of native plants. Cultures such as the Olmec, Maya, and Aztec discovered that latex extracted from rubber trees could be transformed into durable objects when combined with specific natural additives and carefully heated. These materials were used in everything from balls for ceremonial games to waterproof coatings and wearable items, demonstrating a sophistication in material engineering rarely acknowledged in discussions of pre-industrial technology. What makes this discovery remarkable is the chemical principle behind it. The sap in its raw state is sticky, soft, and prone to decomposition. Mesoamerican artisans found ways to stabilize it, producing a rubber-like material capable of stretching, rebounding, and resisting environmental degradation. Modern analysis suggests that they mixed the latex with substances such as morning glory juice, which contains sulfur compounds, and then applied heat in controlled conditions. This process induced cross-linking of polymer chains, a mechanism strikingly similar to the vulcanization Charles Goodyear would codify in the 19th century. Yet despite these insights, the exact methods remain shrouded in mystery. Archaeologists have recovered rubber artifacts with remarkable uniformity in thickness and elasticity, but reconstructing the treatment steps in full detail has proven difficult. The precise ratios of sap to additive, the heating durations, and the environmental conditions, all critical to achieving consistent material properties, are not documented. Ancient workshops left no written recipes, and modern experiments can only approximate the properties of the original artifacts, often falling short in scale, consistency, or durability. Chemical studies have confirmed that sulfur-containing compounds played a role in stabilizing the latex. But even with contemporary techniques, such as thermogravimetric analysis and infrared spectroscopy, reproducing Mesoamerican rubber with the same resilience remains partially unresolved. Some experimental reconstructions succeed in producing small pieces of flexible material, yet fail when scaled to larger ceremonial balls or complex forms, indicating that the original craftsman possessed an empirical understanding of heat, additive proportion, and timing that has been lost to time. The ancient Mesoamericans' mastery of rubber challenges the conventional narrative of technological progress. Their achievements predate European scientific codification by over a millennium. Yet they demonstrate a sophisticated control of natural polymers that modern chemistry struggles to replicate fully. Ancient vulcanized rubber is not merely a curiosity. It is a testament to the ingenuity of civilizations long erased from mainstream accounts, a material that embodies both elasticity and enigma, surviving as a silent witness to the lost knowledge of the past. The Iron Pillar of Delhi is not merely a monument, it is a silent defiance of time. Standing over 7 meters tall and weighing more than 6 tons, this 1,600-year-old column has endured centuries of monsoon rains, humidity, and temperature fluctuations without significant corrosion. For metallurgists and historians alike, it presents a puzzle. How did ancient Indian blacksmiths produce iron that refuses to rust in an environment where modern steel often fails within decades? Crafted during the reign of Chandragupta II in the Gupta period, the pillar is composed of wrought iron with a unique chemical profile. Analyses reveal unusually high levels of phosphorus and exceptionally low sulfur and manganese concentrations. This combination is critical. The elevated phosphorus encourages the formation of a thin protective film of iron hydrogen phosphate hydrate on the surface. Unlike typical rust, which flakes and spreads, this passive layer adheres tightly, sealing the underlying metal and preventing further oxidation. The process is entirely chemical, yet it mirrors the protective coatings sought in modern corrosion-resistant alloys. What makes the iron pillar remarkable is not simply its resistance to rust, but the precision with which it was produced. The ancient smiths lacked electric furnaces, chemical purifiers, or modern temperature controls. Yet the pillar's iron was refined enough to achieve a nearly uniform microstructure, minimizing impurities that could have accelerated decay. Evidence suggests repeated forging, hammering, and careful control of slag content, producing a material with both remarkable strength and chemical stability. Modern metallurgists have attempted to recreate the pillar's composition, experimenting with phosphorus-rich wrought iron and attempting to reproduce its long-term corrosion resistance. While laboratory alloys can mimic the passive layer chemically, achieving the same durability without modern refining techniques has proven difficult. The balance of elements, the specific forging methods, and the microstructural integrity achieved by ancient craftsmen remain largely unreplicated in large-scale construction. The pillar's endurance raises profound questions about empirical knowledge in the ancient world. Its creators understood through observation and experience how materials could resist decay over centuries. No written manual survives describing the techniques. The knowledge was encoded in skill, patience, and experimentation passed from master to apprentice. Today, the Iron Pillar of Delhi stands as both a marvel of metallurgy and a reminder of lost technological sophistication. It is proof that ancient engineers could manipulate chemistry and material science in ways that continue to challenge modern science. For all our advances, few contemporary structures can match the quiet resilience of this silent rust-proof sentinel.